So I want to say just a couple quick words about why the fundamental theorem of calculus holds. So I'm going to start with part 1. And remember, that's the part that said that if g of x is the area so far function, then the derivative of this function is equal to f of x. Or, you know, another way you could have said it is g prime of x is equal to f of x. Okay, so in order to prove this statement, you can actually just use the same thing we've been using all along to prove what a derivative is, and that's the definition of the derivative. And there's a very precise proof in your textbook, so I'm going to give an argument that's a little more hand-waving and more intuitive. So if I use the definition of the derivative, I get g prime of x is equal to the limit as h approaches 0 of, let's see, remember that the definition is f of x plus h minus f of x over h. In our case, this function, I've been calling it g, so I'm just going to replace these with g's. And so if I evaluate the area so far function at x plus h, that just means my upper bound of integration is x plus h. And then I just subtract g of x, which is just my area so far function. Okay, well, if I think about the definite integral as, you know, the net area, then what I realize is, for example, if this is the function f, this is a, this is x, and this is x plus h, then this definite integral represents the area going from, you know, all the way across here. So the area from a to x plus h, and then I'm subtracting off the area between x and a. So I'm subtracting off this part. So this difference really represents the integral from x plus h, or from x to x plus h of this function f. So we're really looking at this area. Okay, now the key is that as h goes to 0, what happens to this area? As h approaches 0, the area, which is given by the area is approximately equal to h times f of x is about equal to the height. Okay, so that's when h is really small. You know, the height is basically going to be approximated by f of x. So basically, this is the limit as h goes to 0 of this area here, which we said is approximately h times f of x over h. And then that's how we get, it just gives you a basic idea of why it's f of x. This part of argument we have to make a little more precise using some different theorems, though. But that just gives you an idea of why part 1 holds. For part 2 of the fundamental theorem of calculus, so why is part 2 true? There are different ways to show why part 2 is true. I'm going to use some theorems from section 4.3. If you recall, we had this one theorem that said if we have a function whose derivative is 0 on an interval, then that function is constant. Right after that theorem in section 4.3, there was a corollary, and that said that if two functions have the same derivative on some interval, then these two functions only differ by a constant. So then f is equal to g plus c, or vice versa. Okay, so these go back to section 4.3. So basically what this is saying is that every antiderivative of f differs by a constant. And that's all. So basically the set of all antiderivatives only differ from each other by a constant. So now we know from the fundamental theorem of calculus part 1 that the area so far function is an antiderivative. It is an antiderivative of the function f. Okay, so this implies that every antiderivative, of f has the form g of x equal to the area so far function plus some constant by this statement. Okay. Now, if this is true, then let's let capital F of x be an antiderivative, any antiderivative of f. Then what we have is that if f is capital F is any antiderivative of lowercase f, then if I try to compute f of b minus f of a, well, I know as an antiderivative that this has to have the form the function f, capital F of x has to only differ from g of x by a constant. So that means that f of a can be written as, or f of b can be written as the integral from a to b of f of t dt plus c minus, and then I'm going to substitute a into this function. Okay, and then what we find is this is just, rewrite it here, and have plus c and minus c, so these are going to cancel each other, and this is just 0 because I'm taking the integral from a to a, and there we have it. That is the conclusion of the fundamental theorem of calculus, part 2. So there are other ways to prove this that are a little more, maybe give you a little more insight into what's going on. But one way to think about it is that, what this is saying is that the area, so another way to think about it, I guess, is that the area under this derivative function between a and b is giving us the net change of the antiderivative function. So we actually saw this previously when we talked about the distance and velocity function, and we found that the area under the velocity function gave us the net change in the position function between time a and b. So it's the same idea as what was happening there.